Okay. A free associative algebra and an algebraically well, it will take me all board and closed. Okay, now I do something which probably not all of you approve. I'll write body. Okay. Algebraical. That was supposed to be Y. Algebraically closed body. Now, just as a homage to my Russian upbringing, I will be using it occasionally instead of a skew field. Well, actually, if you were raised in France, you also can appreciate it. Okay. Skew field. Yeah, skew field is just a field which is not commutative. Okay. So when Toля wrote me a letter and suggested I give a talk, I recalled the story which I experienced once with Amitsur. Amitsur once started his talk by saying, Makar-Limanov always talks about freedom. I rather talk about universality. So that's basically my connection with universality. Okay. That's sort of, yeah. Okay, so let's start with free associative algebra. For our purposes, it's enough for free associative algebra to be of rank 2. So we're familiar with this object, I suspect. Yeah? All words in this alphabet and then. Okay. And think about it as some kind of a non-commutative analog of polynomial ring. Now, when we're dealing with polynomial rings, the fact that we have algebraically closed skew fields, algebraically closed fields, I'm sorry, is very important, and it's rather convenient. The fact of existence is a convenient thing, and I'll illustrate with something. So let me illustrate it with my pet example. It's some kind of a toy Freud-Heizat's theorem, speaking about freedom. Okay. And it's the following. Suppose we have a polynomial here, which does not belong to the field itself. And we're interested in the following question. Is it possible that ideal generated by this polynomial contains 1? Now, this is sort of philosophically important question, because if it would contain 1, then algebra with 2 generators and 1 relation will collapse. 0 will be equal to 1 and kind of bad scenario. Of course, you tell me, well, it's obvious, it's impossible. And, what is the proof which probably comes to mind? You will say, oh, all elements of this ideal look like this, like products like this. Let's recall that we have notion of degree. This polynomial has positive degree. Therefore, this product has positive degree. I cannot express 1 like this. Impossible. Okay. You know what? In order to have a Feuersatz, think about situation when I have many variables. Suppose I have many variables here, and then I can make even better statement, and it will be something like this. Suppose support of P, I'll explain in a second what it is, contains xn. It's a fancy way to say that polynomial depends on xn. Then you can show that intersection of this ideal with whatever generated by remaining generators is empty. And this is real Freud-Heizatz.
Without xn.
Yeah, here we don't have xn. So if this polynomial, about, oh, I'm sorry. You see, I made a small mistake. Yeah, thank you. And this is real Freud-Heizatz. Freud-Heizatz is a whole topic which started with Magnus when he discussed this kind of question for free groups. And so now it's a, well, it's a whole production now. So, okay. So that's one proof. That's one proof. Okay, let's try to think will this kind of proof help us with this question? Can I somehow reproduce this proof in order to show, under similar, of course, restrictions? This is an element here which is not in the ground field. Is it possible that ideal contains 1? Well, if you think about it, then the question is, no. Ideal, not left ideal, not right ideal, not middle ideal. Ideal, you know. As you, again, think about it in the same terms. You have two generated algebra with one relation. Is 0 and 1 in this algebra different? Okay. Well, if you think about it, then you will realize that elements here are written like this. And that's your question. Is it possible to have this equality? And you cannot make it shorter. Of course, in some situations we may, if these guys are linearly dependent or this, but you can write as long an expression as you like, and you cannot make it any shorter. So, well, so big deal. Maybe we can do something about it and work through it. Well, nobody managed. I don't know. Maybe the proof along these lines exists. Nobody managed. And here is a sort of a warning example. Consider element, these are my generators, a, b, a in power n minus 1, where n is your favorite number. To make it impressive, make it large. Consider this ideal. It certainly contains a b minus b. So you have tremendous drop in degree. Let me explain why it is the case. Take this, let me call it, say, f. Take a, b, f. And subtract from it f, b, a. This leading form is cleverly designed, and it will disappear from this. And only 1 will be there. Okay? So if you consider this difference, it will be minus ab plus ba. So, of course, it doesn't mean that there is no proof along these lines. But it certainly shows that if there is a proof, it should be quite elaborate. Okay, do we have another proof in this setting? Yes, we have. And the proof is like this. Consider this polynomial p, say of n variables, to commutative case. And I want to show you another proof, which usually people don't do. Okay, then clearly, since we know that there is an algebraic closure of this field, you can map xi's to ci's. So this polynomial will become polynomial of some constants. And this equation will be 0. It will give you just computationally give you 0. Now, suppose I have something here along the lines. Then the proof will work perfectly well. Because if I can specialize my variables to something to make it 0, then certainly this sum is not 1. So this proof will work in non-commutative case, provided we have a place to find specializations from. And formally for this proof, you don't need an algebraically closed anything. Formally, if you just find for particular polynomial an algebra where you can specialize, get 0, you will be done. But here you have, again, problem. Because how would you know in advance that algebra like this exists? If indeed this ideal contains 1. So it's kind of not quite clear what to do. So I think that if we take as inspirational object complex numbers, then the idea is to build one object which will work for all elements. So something algebraically closed in appropriate sense. Now, what would be this sense? What would be the sense? I think everybody enjoyed the title. I'll erase it and I'll keep something on the board. So in commutative case, we have these polynomials in one variable, and object is field is algebraically closed if for any non-trivial polynomial we can find the root in this field. And of course, historically, let me remind you that complex numbers were the first object with this property. I suspect that before that there was no idea. It's also curious. They appeared in the mid-16th century, complex numbers. And then it was actually Cardano who kind of introduced them. And then people start thinking about them. And then much later, there was this idea of closure. And it's a sad story because I never knew it before I looked at it. That traditionally we think that Gauss was the first to give a kosher proof. It's wrong, apparently. Yeah, it was not done by him. His first proof was with a flow. Then much later he manufactured a couple of good proofs, but do you remember? Yeah. Yeah. Okay. So it's kind of a complicated story. Anyway. So what should I then? What would be a set of my polynomials? Like looking at this example, it looks something like this. So this is the body I'm looking for. So what is the set of polynomials? It looks like we have to think about b of x, where x doesn't commute with anything. Just, variable and no relations. Well, that's not quite the right position, because what we want eventually to do, we want to solve this polynomial by plugging instead of x elements of b. So they better commute with the center of b. If they won't, it doesn't make sense. So here is the, I won't say right definition, I would say possible definition. Consider center of B, consider ordinary polynomials, and take amalgamated free product over this center. So in pedestrian terms, it just commutes only with elements of the center and with nothing else. I suspect that it was Bokut who suggested this definition in the 60s, something like this. Then when Cohn started thinking about these problems, he arrived with many different definitions of what is algebraically closed. This he called PEC, polynomially algebraically closed. He also introduced, I'll just write it because I like it, but I am not going to explain what it is. KEC and FEC, whatever it is. Okay, so this is PEC. And I want to put it on the board and keep it here. So this is the set of polynomials. This is the set of polynomials. So now, what to do? We want to build a field, skew field, a body, whatever, which satisfies. That's certainly a disadvantage here, but big advantage in a plane. Okay. It's certainly. So that's what we want. We want to build something. So how to build a body? How to build a body? Well, you can exercise. What are constructions? What are the known constructions? Now, if you want to construct a field, well, you usually start, say, with a domain, no zero divisors.
Yeah. You want to construct a body
with that every polynomial from this set has root in this body.
Okay.
Just like complex numbers. So the simple-minded analog of complex numbers in non-commutative setting.
Okay.
So what can I do? What would be the result? What are you asking?
What is B?
I don't know. I don't know yet. B is a body which I want to construct, which has the property that it's algebraically closed in this most naive way.
You consider skew product of B on the center.
Over the center, yeah.
You also want B to contain a given skew.
No. Because as we see, if that's what I want, I typically fail.
That's called the bodybuilder problem.
Bodybuilder problem, right, yeah. So how to construct a body? Well, where bodies come from? Well, first example, it was this sad story with Hamilton when he constructed quaternions. After about 12 years of unsuccessful attempts to make something out of three-dimensional space. And we all remember what it is. So maybe quaternions will work. Let's check. Let's check maybe quaternions. And then it would be wonderful, you know, we will be done and that's it. Okay, so quaternions, you remember, I'm talking about real quaternions. Well, we have this element I, which is not in the center, yeah? And I square is in the center. Well, I just write that it's -1. Okay. So which first non-commutative equation which comes to mind? Well, it depends, of course. Yeah. For me, it is something like this. And I will use for shortness this kind of expression. Okay. Well, so if our object is as I want, in these quaternions, I should be able to solve this equation. Okay. Now, those of you who played with Weyl algebra know the following. If you have two letters which satisfy this relation, and you want to compute x with polynomial of y, the result is just ordinary derivative. It's no big deal. Okay, so xi is equal to 1. Therefore, xi square is equal to 2i. Well, it somehow doesn't work, right? Because it's actually x with -1. It must be 0. So here go quaternion. And if you think about it, here go any finite dimensional field. Or I have now first statement. If I have a body like this, its center is algebraically closed. And every element which is not in the center is transcendental over it. I don't know whether it exists, but if it exists, that's what it should be. Okay, too bad. What was the next example of a body? Do you know? What was the next example of body? Huh? After quaternion. Well, it happened to be infinite dimensional. It was Hilbert's example. Hilbert, when he was working on his geometry things, realized that algebraic properties translate to this Pappus, Desargues, whatever. So he needed an example of an ordered field with unusual properties. Basically, non-Archimedean, that's what he wanted. And he built the field. Now, according to, there is this wonderful paper by Cohn, which is called probably All What You Want to Know About Bodies But Was Afraid to Ask. Some different title, but sense about this, yeah. Hilbert made, Paul Cohn. Paul Cohn, yeah, of course, yeah. Paul Moritz. Hilbert curiously made a mistake in his first paper devoted to it, and then I saw it already in Hilbert and Confossen where it's correct, but so I didn't know. So what he did the following. He considered, I don't remember, was it over complex or over reals? Well, never mind. He considered all Laurent series. So what? Probably I should write something like this. So all power series in one variable with negative degrees, it's easy to show that it's a field. Then on top of it, on this field, he constructed another Laurent series with one additional variable. And he introduced something like quantum plane relation. He said that ST is equal to 2TS. So according to Cohn, in the original paper, it was ST equal to minus TS, which is no good. First, or second of all, it will be finite dimensional over the center. But first of all, it is not order preserving. So his construction would collapse. So this is wrong, this is right. And so, in fact, you can prove that if you have this power series of power series. With this relation, you have a body. So we can call it Hilbert's body. You see, there is some advantage in this terminology. Okay.
The 2 can be changed on any.
Of course, of course, So this is Hilbert's body. That's wonderful, and it is strikingly different from quaternions for the reason which was mentioned. It's infinite dimensional over the center, and we know now already that
C or R?
it doesn't matter, any field. It's not important.
You
Oh,
algebraically.
you want, okay, great. Let's put C in order to have a hope that it works, okay? That it works. Do you want me to check? Okay, let's check whether it works or not. Okay, so of course I will check the same equation because I like it. It by the way has special name. It's called metro equation. Metro. Now, of course, if you don't know the story, it's impossible to guess what's the reason. The reason is that Amitsur and Cohn were together in Paris. And I somewhere have exact date because Cohn remembers it, where they were discussing this kind of questions, and they arrived to this equation. And that's why Cohn sometimes called it metro equation. Or should I say called, because unfortunately, as Amitsur, they both already in greener pastures. Okay, so anyway. Well, let's check. So suppose I have some expression, and I don't care, I'll write it somehow. So I have this 2 power series, A, B. I want some couple of power series here, and I want this to be 1. Now, what will give input into 1? Let's think. So if I have here S in power I, T in power J, right? By what should I multiply it in order to get constant? I can rewrite because of this relation, I can think that S is, okay. It should be S in power minus I, T in power minus J. Right? Because cancellation, forget about 2. It's like cancellation goes. Okay. So if you think about it, you have a trace in this situation. Coefficient with 1 is a trace function. So in fact, if you look at coefficient with 1 at this expression, it will be always 0, no matter which power series you will choose to input there. So Hilbert is not good enough, right? Unfortunately, at least for this one, Otherwise, of course, Hilbert is great. Okay, so where to look? Where to look? Now, there are very few constructions of bodies, in fact. I counted roughly 4. And 4 is kind of a rather dubious one. Finite dimensional we disposed of. So what would be these constructions which I think about? So first construction was Ore's construction. Construction by Ore. And construction by Ore was motivated by this desire to have this construction of rational numbers, our integers, somehow transferred to non-commutative setting. This is the same construction as with any commutative domain works, right? And where is the difficulty? Well, first difficulty, of course, how to write this, or maybe something else which we cannot imagine. Well, suppose we decided to write it like this. As we know, when we're dealing with fractions, multiplication is much simpler operation than addition. Addition is complicated. But what to do here? I cannot multiply. If I write expression like this, I have here wrong direction. So what I need to have is ability to rewrite it correctly. Right? Something like this. If I can do it, then I am in here. So, well, I cannot really write this kind of a relation for my ring because I don't have these elements. But luckily, I can rewrite it, right, as CB1 is equal to BC1. So what do we have here? Something is wrong. Yeah, we have this and we have this. supposedly we can find these two guys. And of course, we don't want it to be equal to 0. So this is easy to rewrite. C multiply ring intersected with B multiply ring is not 0. Is not just 0. Yeah, Vanya already put me. Yeah, otherwise I would write empty. Yeah. Okay. So this is ORE condition. In principle, you can check it. And actually, it is checkable in many situations. And then you can build the whole construction. You just transfer it of a skew field or of a body. Yeah, so you're just considering all expressions like this. And just like in a commutative setting, you can prove that it's indeed a body. If this condition is satisfied. This is left order condition, right order condition. There are curious rings where one-sided condition is satisfied, other side is not. It's interesting.
Where is left side?
If I write in this instead of these fractions, then corresponding condition would be like this. For all C and D. For all C and B, well, we can ask them not to be 0, but such that CB is not 0. Okay. So, good construction. Good construction. So that's one of the constructions which is available. Great. So what I can say about that? I'm not going to check it, whether such a construction work, because it won't, and it will be a bit too tedious. So let's move on, and what would be next possible construction? So next possible construction actually was, it was a Hans construction in the beginning of 20th century, but it was abelian construction. Namely, he was concerned with putting abelian groups inside of fields. It means that, that if I take, let me be more precise. If I take some nice familiar field and then make some fudging with it, with this construction, it doesn't work. But if I do this for nice field countably many times, it will. Yeah, but we will come to it. Okay, so next construction is kind of a generalization of Hilbert, not quite. There is some substantial feature which is different. In a sense, maybe it's a far-fetched sort of generalization of a group ring. So if we have a group, there is this nice object group ring. So how to manufacture a body out of this material? It turns out that you can do it if G can be linearly ordered. If it's linearly ordered, yes, of course, it should be linearly ordered, not as a set, as a group. Which of course means that A is less than B implies that CA is less than CB as well as AC is less than BC, okay? Then you can manufacture infinite power series, which would work. In order to do it, well, you can think about it, depending on your point of view, you can think about either as functions from G to F with special property and L, or just as, I don't know, probably it's more convenient to think about it as power series. Okay, so the question is where to choose those G for which coefficients are not zeros. And the answer is in well-ordered set. If you have a set which is well-ordered in our linear order, then it would work. It's not actually Hans checking works more or less verbatim in non-commutative setting. There is some difficulty here when you're checking Archimedean case versus non-Archimedean case. It sort of raised the level of difficulty, but even this is present in commutative case. all collections like this, where G belongs to support, let me call it F, support of F, and this support is well-ordered set. This is a body.
But F is fields or body?
Hmm?
F itself.
F is a field.
Yeah.
G is a group.
Yeah.
Collection of all this power series is body. And it's not hard to show that it's a body. It's not hard to show that it's a body. This body, by the way, has a curious property which is sometimes handy. It satisfies so-called lemma on radical, which is not usual radical which comes to mind when algebraists talk with each other, but radical from high school, you know, like square root. And the property is the following. Things like this have valuation, natural valuation. That's the smallest element in the support. So if I have this, then if G in power 1 over n belongs to our group, then F in power 1 over n belongs to our body. It's enough, and it's just, you know, this Newton binomial theorem, nothing else. Okay, so that's a nice construction, but we already rejected it. Why? In this situation, you again have trace function. Trace function, coefficient with 1. So whenever you take commutator in this kind of set, coefficient with 1 will be 0. So again, it doesn't work. Again, it doesn't work. Again, it doesn't work. What was the third one? Third one is beautiful construction, which allowed to prove, I would say, the most important theorem about bodies, but it's not very suitable for computation. This is construction of Cohn, who did the following. It's sort of really wonderful generalization of Ore construction. So what is Ore construction? We take R, we throw on top of it all inverse elements of R, so we don't invert 0, and under certain conditions, which are easy to formulate at least, if not to check, it's a field, it's a body. Now, by the way, speaking of these conditions, there is the following curious way to check that Ore condition is satisfied. Suppose it has the following property. Any two elements in your ring don't generate freely a free algebra of rank 2 over the center. If this is the case, Ore condition will be automatically satisfied. It's a simple computation. It was observed more or less simultaneously. If you write the relation, you can fudge it a little bit and you will get. Okay. So it's kind of, so it tells you what immediately. If you know what is Gelfand-Kirillov dimension, everything with finite Gelfand-Kirillov dimension would work. Or take finite dimensional algebra, take universal envelope, it would work. Or take a group ring, here you have to be careful, for torsion-free nilpotent groups, it will work. For solvable, it already doesn't because the growth is exponential. So wherever growth is polynomial in a group, it would work. So it's kind of curious. Okay, anyway. So what was the idea of Cohn? Idea was the following. If we have a matrix of full rank, it can be reformulated like this, that if I have a matrix and I try to write it as product, so this matrix is n by n, and this is n by r, and this is r by n. So whenever I can write equality like this, where r is less than n, it means that rank is at most r. So he considered all matrices which cannot be written like this. He called them full matrices. He formally inverted all full matrices. He put all results in the soup and told under certain conditions, which are called free ideal ring. Again, some checkable condition, which is less easy to check than, okay, kind of checkable. Now, this is a beautiful construction which allowed to prove the following statement, which is trivial in commutative case and highly non-trivial in non-commutative. Let me formulate it this way. If you take two algebraic elements over a field, their sum, as well as their product, is algebraic. And you can put them in some over field. Now, this is certainly wrong in non-commutative case. But if you ask the following question, suppose I have a field and I have algebraic element over it and another algebraic element over it, which are sitting in different bodies. Can I put them in one body? Yes. And that's this theory of Cohn allowed him to prove this theorem about product. So that's really very non-trivial result, that if you have two bodies with, say, common center, you can put their amalgamation in a body. And I think that just the most difficult theorem in this and the most important theorem in all this theory. Okay. Well, God help somebody who wants to compute something with this construction. Okay. Now we come to the fourth construction, which is kind of a loosely defined and which actually will deliver.
Construction doesn't help you.
No, because it's a beautiful construction for proving theorems and for developing theory. But if you want to compute something, it's not clear how to do it at all.
So it's not, doesn't clear if it's work, as I understand.
Well,
You already said that what you're trying to do would be impossible in general anyway, so that this construction would be designed to do it all the time if it were going to work at all.
it's so. If I want, say, suppose I want to find solution for metric equation with help of this construction, I don't know. I'll be kind of lost. I'll be kind of lost. So fourth construction, it's kind of a mixture of Ore construction, fudged Ore construction, which Ore invented, and this infinite power series business and whatnot. So, to make situation more entertaining, Ore realized that he can take a polynomial ring over a ring, but skew multiplication. And well, as I wrote it, it commutes, but in a moment it stops. So this is just ordinary polynomial ring with ordinary addition and ordinary multiplication. And then, of course, if R is commutative, so the result is commutative. So how to make it non-commutative? Well, modern language is called deformation. Take multiplication on R, leave it as it is. You cannot help it because you don't know anything about it. But if you want to, well, for me, polynomial usually with coefficients on the left. So if you want to rewrite it, you won't write it like this. But you apply something to R and then add something to this, which depends on R as well. Now, this is kind of a construction which is similar in a sense to power series construction, because this is again a situation with valuation. That's what is important in all this. You have evaluation. Here, evaluation is just degree relative to x. Now, you have to be careful. You cannot throw anything here if you want your object to be associative. But it's no big deal. Say, for example, you can, not necessary, but if it's automorphism of R, and this is a derivation on R, it will work. And you can relax these conditions quite some. But there are some conditions in order to have it associative. OK. Now, probably the most familiar example of Ore construction is so-called Weyl algebra, which goes under many different names. And in this situation, alpha of R is just identity. So just R. And beta of R is some derivative applied to R. So for Weyl algebra, we have to take R to be a polynomial ring in one variable, and then this will be just ordinary derivative. Okay. Then you will get. Yes, yes, of course, yeah. It's small enough to satisfy our condition. Yeah, it's. Yeah.
The Ore condition means
that condition, yeah. That's no big deal. Okay, so.
In that case, R was not
No.
and you computer.
It's just because I'm stupid and using the same notation for different things. Yeah. Of course, yeah. And you also can fetch, you can take not a derivation, but sort of called alpha derivation. But it's very simple-minded conditions. It's easy to write them. It's no big deal. Yeah. Okay. So you remember our major trouble was with this equation. It is first time that we can actually solve it. In this case, yeah, because in Weyl algebra, that's what it is, It's Weyl algebra is something with two generators which satisfy this relation. We have a wonderful news. We proved with you that this ideal generated by AB minus 1 does not contain 1. Because okay, I'm actually cheating a bit. But if I tell you that if I take a ring of polynomials and one variable and I take two operations, one is multiplication by x, other is derivation by x, then they satisfy this relation, and then I have a subalgebra of homomorphisms of this thing, in which 0 is not equal to 1. Aha, here it is.
But why you didn't start from Weyl algebra, in which this is
Well, because, I want to build up a suspense. Okay, now, so let's collect what we know. So we have this body. We have the center of the body. We certainly want it to be non-commutative. By the way, if you look at this definition, if B is the same as center, it's ordinary definition. It's just ordinary definition of algebraically closed field. That's another reason why I like it. Okay. And I certainly have an element here. Let me call it somehow. Well, you know what? Let me call it P. An element P, which is not in the center. And as we know, it is transcendental over the center. Not. It's transcendental over the center. And so I should be able to solve this equation in my field. And here I have it. Okay. So if I have the body which I like, what it should contain? It should contain P and any power of P. Of course, only fractional powers are interesting. It should contain Q and any fractional powers of Q. So I cannot have anything smaller. Okay, now how to manufacture, say, out of this material an algebra? Not body, just an algebra. What to do? Well, it's no big deal, because if you worked with Weyl algebra, you know that you can perceive elements of Weyl algebra as ordinary. I cannot draw a star, so that's why I'm drawing this asterisk. Ordinary addition with multiplication given by some formula. It is called star multiplication oftentimes. And in the right side, it's usual multiplication of polynomials. And here you have partial derivatives, whatever. And you can perfectly well use this formula on what? On the following object. If you consider, well, let's say complex numbers, not important. You consider this power series which I have to define. So the easiest way to do it is the following. Take two copies of Q as a group with which you start your Maltsev-Neumann construction. Take an ordering, say lexicographic ordering given by this, that P is much smaller than Q, which is smaller than 1. Consider all power series with well-ordered support. And then use this multiplication. Of course, you have to work a little bit to prove that it would work, because now you have additional terms, but they converge, no problem. And that would be a nice algebra. And that would be also a nice explanation why I know the answer about the body. I didn't tell you what is the answer. The answer is yes. if characteristic is 0. And I wish I know if characteristic is positive. Okay. The reason is that one reason is kind of rather lame. We have inverse factorials, which is hard to compute in finite heuristic. It's not really a reason, because these derivatives will cancel it.
So the yes or no, the question is whether there's a non-commutative object with these properties.
Yes, exactly. Yeah, that's the question. You have, that's no big deal, but here is a more serious problem. Suppose your characteristic is 2. Now, what is P commuted with Q in power 1/2? Well, I know what it is, right? It's 1/2 Q in power -1/2, which works perfectly well in any characteristic by 2. In characteristic by 2, it doesn't work, which means it's not that I cannot write this element, but this element certainly doesn't commute according to these rules. It becomes more complicated. The base here for this kind of consideration is that if you have a field of characteristic kappa, then x in power kappa commuted with y is the same as adjoint action, this commutation, applied kappa times to y. The result will be the same. You have some binomial coefficients which cancel out, no big deal. But the big deal is that you have to join a lot of new elements. And I don't know how to do it, and I asked several people to work on it, and too much, just too much. Okay, so are we done? Are we done? Maybe that's the object. Osia? We don't, we're not. And the reason is the following. Suppose you want to solve equation, now you have P and you have Q, and you want to solve equation Px is equal to Q in power -1. Well, what should be a solution? Well, we know if we forget about algebra and recall our calculus, then, you know, it is something like natural log of Q, which satisfies this. And natural log of Q is not algebraic element. You have to join it. And you don't have any choice here. You see, that's kind of interesting. The construction is rather loose. Okay, in my body, we have P, we have Q, which satisfies this relation. PQ is 1.
Yeah.
Suppose I want to solve now.
Yeah, but what do you want in order to say yes?
I want to be able to solve any equation, which comes to my mind, to your mind, you know. With coefficients, I just don't want to be stupid enough to solve equation like this, you know. This I don't want to solve, no. But P and Q are not in the center. I have legitimate equation. I have to be able to solve it. Here comes log. Of course, you also have similar situation. Log of P. Are we done? No. Because you have to add iterated logs. But when you add them all together and cook it a little bit, you have to cook up it a little bit. You will get something which turned out, after rather tedious proof, algebraically closed. So the answer is yes, but specifically in 0 characteristic. That's one point which I want to bring to your attention. And another one, that though the construction is rather loose, it's not as loose as it seems. So it has some kind of universality in it, right? You have to have whatever you have. Now, how you assemble these elements, it's a different story. And actually, after my example, there was some kind of simplified example by a guy named Kolesnikov, who considered a bit bigger field. And just to illustrate what we're talking about, let's retract before I finish. Let's retract to commutative case. So what we're having in commutative situation? In commutative situation, a typical question, we have a polynomial ring, or field of rational functions. What is its algebraic closure? Actually, this question was answered by Newton, although we don't think about it in these terms. When he introduced his Newton polygons and some procedure, okay, he got answers. Now, what is curious? You can look at Hans construction over Q, But you can restrict yourself to a smaller object. Namely, you can consider only power series in x in fractional powers, such that denominators for every particular x are bounded. They depend on x, but they are bounded. And it is easy to prove that in Newton construction will give you exactly this kind of thing, though there was later a rather confusing discussion of this by Puiseux, and these power series, for completely wrong reason, I think, are called Puiseux reasons. Now, the only thing which I can say for Puiseux that he was also concerned with questions of convergency. If you look at it from purely algebraic point of view, it's just confusion. Yeah, but in this sense, Newton is much, much better. So, be as it may, are all power series with this bounded? No, of course. You have some restrictions on coefficients, but it probably would be not very solvable question. I don't know. Well, there are some descriptions. They should satisfy some recursive relations, these coefficients. But it's not easy to, especially when you're dealing with power series, what you're dealing with finite length, initial interval. So, you don't know. So, be as it may, here is my report. Now, what was the purpose of it? One was, to answer Tolya's request. And the other is to attract your attention to this really fundamental problem, which probably nobody cares, but it doesn't make it less fundamental. Why, if you have a free algebra over a field of finite characteristic and a non-trivial element here, why this ideal does not contain one? Why two generated algebra with non-trivial relation produce a non-trivial algebra? It is something which should be answered, and the answer is it is true if characteristic is 0, and we don't know if characteristic is finite. And that's kind of an unsatisfactory situation. It's still open question. It's still open question. Now, if you actually want to solve it, I can give you a toy problem, which, yeah. Yep. Okay. So that's the best way probably to approach it. And the way is the following. Consider this equality which we're trying to disprove. So what we have this equality, okay? Where f is a given element of free algebra. Consider the following construction. Consider f computed on two matrices where A and B are matrices of size n, okay? Consider rank of it, okay? With every pair you have a rank. Consider minimal rank. Minimal rank achievable. Of course, if this guy doesn't have free term, it is 0, and we're done. But of course, if there is no free term, no big deal. Yeah? So you have some number, R of n. What's the behavior of R of n as function of n? It should behave like this when n goes to infinity. In fact, I suspect that it behaves even better. It increases for some time, and then it flattens out. But I cannot prove it. Now, suppose you can prove this. Then you're done. Because you take sufficiently large n so that conditional rank is less than 1 over n, and you will never add it up. So that's maybe the best problem if you are just concerned with this question. But if you are concerned with these bodies, then it won't work. Yeah. Okay. That's it. Thank you.
Very interesting story. Please tell me, when did you suggest this?
It was somewhere in the 70s where I published a very short note which contained nothing, just declarations. And in 85, there is a rather unpleasant for reading paper. Yeah,
And the paper by Gelfand and Kirillov about the ratio for universal,
it is 60 something. No.
No, I understand that this is not solution of your
problem. No. That thing, their conjecture it was 68 maybe, or maybe even. Was it before Diximier or after Diximier?
It was before, or I think.
It was. I think it was before. It was before the 68, before Diximier work.
Okay, so
Okay.
Anyway, it doesn't. But some connection, maybe the answer can be embedded in your.
Oh, that's of course true. Yeah, no. This thing may contain no. This is really a huge body. You can put a lot of things in it. Say some examples when you have. Well, how do you look at deformation? As dynamic process or a static process? You have two different points of view here. So you can actually put. I think I experimented with the following. I looked at quadratic brackets on three-dimensional space, and so they're all possible to quantize them. Okay. Now, what you can do, you can have, this paper was with Donin, so there was a Donin's part and my part. So his was philosophical considerations where you can prove it philosophically. And my part was just to find sort of sub-skew fields in this object which satisfy all relations. So it's a good object, and people are actually even trying to use it, but it's all too obscure.
Almost universal.
It is almost universal. Yes.
Please.
As far as I understood, there are several possibilities to get such.
Oh, certainly, yeah, because when you are gluing these logarithms together,
Yes.
you have to glue them in such a way that your resolution process will work. Because, you have some object, you're trying, how you're doing it, how Newton was doing it, coefficient by coefficient, method of undetermined coefficients. It works here the same. The difference is that you have to solve some differential operators, find solutions for some, whatever. And now, if you are not careful, you will get carried away. It will be too long. So you have to fudge this. And of course, there are many different ways to glue these things together. But what I was trying to say, and I think it's now obvious, that all these elements must be there. Yeah, but that's basically what it is.
Yes, now my question is, among all these possibilities, is there kind of
The possibility,
choice in some sense whatsoever?
I don't think so.
Okay.
I don't think so.
Maybe finish with our session, and thanks again to speaker for another.
Okay.
Late again, and let's start at not at 2 but 2:30. Okay, it will be even better because we have no break.
All yours. Can you undo me?